The Big Bang is a lie, physics just broke. Hey, get this. The Big Bang timeline just slipped. JWST pulled back the curtain and caught bright, heavy galaxies lighting up the sky when the universe was barely out of the delivery room. The numbers didn't blink. If those masses hold, the schedule we trusted is wrong. But here's where it gets interesting. In 2025, strong lens clocks from Tokyo pushed the Hubble tension harder, and even a 2024 tired light claim tried to kick the ladder. I'm telling you, something's off. In the next hour, we'll stress test the galaxies, the math, and the fixes, and see if the beginning ran faster or if our ruler's been shaved without us noticing. The impossible galaxies. Start with a room that smells like coffee gone cold. A small team sifts through deep fields, CERS, JADES glass, searching for the faintest red smudges. Photometry puts them at redshifts 10, 12, 15. Translation: we're looking less than 400 million years after the Big Bang. Then the FITs return stellar masses flirting with 1 billion suns or more and star formation rates like factories on double shift. The channel goes quiet. Someone types, "Too big, too soon." Here's why that phrase stings. In the standard lambdictum playbook, tiny fluctuations seeded by inflation grow under gravity. Dark matter halos collapse first, gas cools, stars ignite, feedback throttles the frenzy. It's not leisurely, but it's not instant. By Z10, you expect scrappy, blue, low-mass clumps, not mature systems with dense stellar bulks and rest-frame optical light strong enough to fake middle age. So the first question is basic. Are they really that far? Photometric redshifts can lie. Strong emission lines can boost flux in filters, dust can redden a closer galaxy into a distant imposter, and active nuclei can masquerade as mass. Teams sprint for spectroscopy. Lyman breaks, nebular lines, clean features that pin distance. Some candidates slide down to Z57 after spectra. Others hold the line. A few even push higher. The universe breakers don't disappear. They thin, then regroup. Next comes mass. Photometry infers stellar mass by fitting spectral energy distribution. Essentially, what mix of stars best explains the colors. But if nebular emission fills the bands, you overcount starlight. If the initial mass function is top-heavy, you overweight big stars. If a hidden AGN contributes, you inflate the total. With better modeling, allowing strong lines, bursty histories, and AGN components, some masses tick down. Yet a stubborn subset stays hefty. As of 2024-2025 analyses, catalogs still show roughly twice as many massive systems at these epochs as baseline lambdictum simulations predicted. The panic softens into tension. The schedule is tight, not shattered. Now surface brightness. Redshift dims a galaxy's brightness by 1 plus Z4. High Z disks should look tiny and faint per unit area. Early JWST images showed larger than expected apparent sizes for some candidates. Lensing can magnify and stretch, hiding foreground tricks. Survey teams remeasure with careful lens maps, some shrink. But even after debiasing, bright overperformers dominate the catalogs. That's selection. We see the luminous tail first. It doesn't erase the tail. Why too big, too soon matters isn't just star counts. It's chemistry. Metallicity rises as generations of stars live and die. Seeing relatively enriched gas early implies fast cycling, stars forming, exploding, seeding, and reforming on compressed timescales. It's also surface brightness and compactness, tight stellar cores hinting at rapid assembly, possibly through gas-rich mergers or violent disk instabilities. What fixes help? Efficient physics at dawn. Metal-poor gas cools via molecular hydrogen and fine structure lines. Under the right conditions, it fragments hard, feeding extreme starbursts. Early black hole seeds, remnants of massive population III stars or direct collapse candidates, can accrete, their feedback compressing or clearing gas in cycles that actually hasten growth. Subgrid models in simulations, those compressed rules for unresolved physics, get retuned. Stronger early cooling, burstier star formation, anisotropic feedback. The result? Galaxies that build faster without breaking late-time statistics. Meanwhile, observers hedge their bets with alternative levers. If the present expansion rate h is higher than CMB inferred values, the look-back time to a given redshift shrinks. A faster clock makes impossible growth less impossible. That's the Hubble Tension's shadow creeping into dawn. But even with a modestly shorter timeline, you still need efficient channels. Lensing and selection effects sit on the witness stand. Strong lensing can boost counts and brightness, biasing catalogs to rare, magnified systems. Survey teams cross-match with mass maps to flag the culprits. Some early headliners fall into this bucket, others don't. The net: corrections help, they don't acquit the schedule. Here's a micro story that humanizes the curve. A grad student stacks cutouts of a candidate at Z-13, heart thumping as the pipeline returns a clean Lyman break and no obvious low Z solution. Weeks later, the spectrograph delivers a line faint, but right where it should be. Her mass estimate drops after she includes nebular contamination. The galaxy is smaller than the first fit. It's still bright. It's still early. She doesn't pop champagne. She updates the plot and adds a footnote: efficient physics required. There's an irony tucked in here. The same lambdictum that nails the acoustic peaks in the cosmic microwave background and the clustering of galaxies at low redshift can, with modest retunes, absorb faster early assembly. Tilt the scalar spectral index within bounds, adjust sigma 8 slightly, allow for higher early star formation efficiency in dense halos, and your simulations spit out more luminous juveniles. The scaffolding doesn't collapse, it flexes. So what still stings after the dust settles? The ledger of early light. Even with corrected masses, careful sizes, and conservative fits, the bright tail is crowded. The number density of massive, compact systems appears elevated. Chemical clues hint at quick enrichment. Surfaces shine harder than naive models expected. That doesn't mean the Big Bang is false. It means the first chapter read faster, the pen wrote with a finer nib, and our subgrid notes were too simple. Which sets up the next move cleanly. If the late-time anchors of lambdictum are firm, maybe the crack sits closer to the opening pages. The initial conditions, the inflationary seeds, or the way we translate photons into histories. And if the cosmic clock itself is off by a few beats, those galaxies stop being miracles and start being milestones. The 13.8 problem: how we nailed the age. To see where the schedule came from, you have to stand in a control room built out of fossils of light. The number on the whiteboard, 13, 8 billion years, wasn't guessed. It was triangulated, pinned down by 3 independent yardsticks that don't share the same weaknesses, then cross-checked until the error bars stopped shrinking. Start with the oldest messenger, the cosmic microwave background. Freeze the universe about 380,000 years after the Big Bang, when electrons finally married protons and light could travel. That light, stretched into microwaves by expansion, arrives today as a near-perfect blackbody with tiny temperature ripples. Plot those ripples into a power spectrum, and a comb of acoustic peaks appears. Those peaks are sound waves in the photon, baryon plasma, imprinted at recombination. Their positions and heights encode the matter content, baryon fraction, curvature, and expansion history. Feed that to lambdictum and you get a tightly constrained set of parameters. One of them, when evolved forward under the model's rules, gives you the current expansion rate, and by integration, an age. Planck's data favored an age right around 13.8 billion years, and a present h near 67 km/s/MPC. That's one leg of the stool. Next, fold in baryon acoustic oscillations, those same primordial sound waves, now fossilized as a preferred clustering scale in the distribution of galaxies. Map millions of galaxies in 3 dimensions, and you find a subtle excess of pairs separated by about 150 megaparsecs. That scale is a standard ruler. Measure it at different redshifts, and you get the expansion history in discrete slices. Bow doesn't care about supernova calibrations or stellar physics in distant hosts. It tracks geometry. When combined with CMB constraints, it nails down the distance, redshift relation with impressive precision. The ruler agrees with the microwave sky about the overall story and, crucially, the age. Finally, bring in standard candles. Type Ia supernovae, white dwarfs ripped over a mass threshold, explode with remarkably similar peak luminosities. Calibrated properly, their brightness becomes a distance indicator. Plot distance versus redshift, and you get the signature of acceleration that led to dark energy, the lambda in lambdictum. The supernova Hubble diagram alone can't give you an absolute age without assumptions, but when you anchor it with local distance ladder calibrators, Cepheid variables, the tip of the red giant branch, and compare with BAO and CMB, you lock the story together. Multiple ladders, different rungs, converging on a consistent timeline. If you're keeping score, this is why cosmologists don't panic easily. The CMB acoustic peaks, BAO measurements, and supernova distances are independent lines of evidence that fit a compact model with few parameters and wide reach. Adjust one lever, and the others respond in predictable ways. You can quantify the age because the framework tying these data together is not a jigsaw puzzle with pieces forced to meet. It's a differential equation with well-measured inputs. But here's the caveat: the late-night Slack threads circle. Agreement depends on early universe assumptions. Inflation smoothed the initial conditions and set a nearly scale invariant spectrum of primordial fluctuations. The sound horizon at recombination, the physical size of those acoustic ripples, depends on the energy content and expansion rate before and during that era. Change the early recipe, and the ruler you've been using shrinks or swells. Early dark energy can punch the expansion briefly, reducing the sound horizon. Neutrino physics can tweak the radiation density. Even subtle features in the inflationary potential can imprint small deviations that propagate into present-day inferences. That's where the 13.8 becomes less like a birth certificate and more like a contract. Within lambdictum rules, the number is solid. Step outside the rules, and you're renegotiating the terms. The Hubble tension lives exactly in that space. Local measurements, distance ladders, and time delay lenses prefer a faster expansion today than the CMB-anchored model implies. One way to reconcile them keeps the late universe intact, but alters the early chapter, shaving the ruler to let both sets of data fit. A shorter sound horizon means you can hold the microwave background in place and still allow a higher H. The integrated age can shift slightly without demolishing everything else. Meanwhile, caution signs blink. Some JWST-assisted calibrations of local distance indicators nudge values in different directions. Reanalyses of Cepheid hosts, the use of red giant branch tips, and lensing-based H all try to avoid shared systematics. The trend holds. Late time probes point higher, early time probes point lower. The stubbornness of the mismatch is the point. If you can't make it go away with reasonable systematics, you're forced to ask if the early assumptions need revision. None of this rescues every oversized galaxy on its own. Even with a slightly younger clock at a given redshift, those bright outliers still demand efficient formation. But it reframes the rigidity of the schedule we thought we had. The age came from a chorus. The harmony remains, but one section is singing a different tempo. So when someone says the universe is 13.8 billion years old, the honest addendum is under the lambdictum score. The strength of that statement is how many instruments are in tune. The opportunity, the crisis, if you like, is that the few out-of-step notes might be telling us the opening bars weren't quite the ones we printed. Inflation's promise and its blind spots. To see how the first pages could run faster without wrecking the ending, you have to sit with the wildest quiet idea in cosmology: inflation. Not an explosion, but a blink of accelerated expansion that takes a tiny, causally connected patch and stretches it until regions that once shared a thermometer now sit billions of light years apart. That single move solves 3 headaches at once: and sets the stage for everything we measure later. Start with the horizon problem. The cosmic microwave background looks uniform to 1 part in 100,000 across patches of sky that, under slow expansion, could never have exchanged so much as a photon. Inflation says they did before the stretch. Those regions were neighbors. They equilibrated, then got pulled apart faster than light can knit them back together. Uniformity isn't a miracle, it's memory. Next, flatness. General relativity allows space to curve like a saddle or a sphere, but precision maps show our universe is very close to spatially flat. Inflation irons curvature the way tension flattens a wrinkled sheet. Enough E folds and whatever bend you started with dilutes to nearly zero. You do fine-tune initial curvature, you erase it. Then the seed problem. Where did the tiny over and under densities come from? The ones gravity would later amplify into galaxies, clusters, and voids. Quantum fields can't sit perfectly still. They jitter. During inflation, microscopic fluctuations get stretched to astronomical scales. Modes cross the horizon and freeze, leaving a nearly scale-invariant spectrum of perturbations. After inflation ends and the universe reheats, those ripples re-enter the horizon. The photon baryon plasma rings like a drum, imprinting acoustic peaks in the microwave sky. The statistics, almost Gaussian, slightly tilted, match what telescopes see. That's not hand-waving, it's a predictive fingerprint. There's beauty here. A small set of parameters, the amplitude of fluctuations, their tilt, the baryon fraction, the matter density, describe both the speckled microwave wallpaper and the large-scale structure scaffolding. Inflation, as a class of mechanisms, links the smallest physics we can't see directly to the largest patterns we can. But the pen that writes neatly also smudges. Inflation's successes arrive bundled with blind spots. The first is the engine. In the simplest stories, a scalar field, the inflaton rolls down a flat potential driving accelerated expansion. We don't know what that field is. Many potentials can do the job. Whole families survive current constraints. Flexibility lets inflation accommodate data. It also makes specific predictions slippery. If dozens of models fit, which one, if any, is right? Look for a decisive signature. Primordial gravitational waves. Inflation stretching spacetime itself should launch a background of tensor modes that polarize the microwave background in a curl pattern, B modes, on large angular scales. Experiments have chased that signal for a decade, setting upper limits that squeeze large field models where the inflaton traverses big distances in field space. So far, no confirmed detection. That's informative. Many versions get pushed to the margins, but it's not a kill shot. Then there are the anomalies that cling to the low multipoles. The quadrupole power sits low. Some alignments in the largest modes, the cheekily named axis of evil, won't quite die. Hemispherical power asymmetry lingers at low significance. These could be statistical flukes in a vast sky. The look elsewhere effect is merciless. Or they could whisper that inflation wasn't perfectly simple, that the potential had a feature, a pause, a bend that left a bruise. The data don't force a rewrite. They do keep theorists honest. Another concern, initial conditions. Ironically, a mechanism designed to wipe away sensitivity to the start seems to require a patch where the inflaton field is already smooth enough and high enough on its potential to begin rolling. Some argue that in a messy quantum gravity prelude, such patches are natural. Others aren't convinced. It's an argument about measure in a space of possibilities we don't yet calculate from first principles. Push further and you hit eternal inflation. In many models, while our patch exits inflation and reheats, other regions keep inflating. Quantum fluctuations kick the field uphill as often as down in some domains. The result is a bubbly multiverse where pocket universes like ours nucleate endlessly with different low-energy properties. It's a legitimate mathematical outcome of certain potentials. It also raises a testability problem. If most of the structure lies forever beyond our horizon, how do you confirm or falsify the picture? People have hunted for bubble collision scars in the microwave background. Nothing definitive, Maybe they aren't there. Maybe the signal's too faint. Maybe our patch is lonely. There's also a practical blind spot tied to the very success you admired 2 minutes ago. Because inflation can generate the right spectrum of perturbations across a wide range of potentials, you can tune details to fix mismatches at the edges, small features to explain a dip, gentle running to ease a tension, without clear guidance from fundamental physics. It's a flexible pen. That's a virtue until it becomes a vice. So where does that leave the too fast at dawn problem? If the seed's inflation set were slightly different, if the tilt favored a bit more large-scale power within current bounds, if non-Gaussianity on small scales were just enough to enhance early collapse without violating constraints, you'd help dense halos form sooner. If reheating left pockets with unusual thermal histories, you'd tweak cooling. These are not free passes. They're levers within a framework that already matches most of what we see. The honest read is this: inflation earned its place by solving old problems and predicting new structure that we later measured. Its blind spots aren't fatal, they're invitations. The decisive tests, B-modes, small non-Gaussianities, features, are coming with sharper instruments. Until then, treating inflation as the default doesn't mean pretending it's done. It means letting its economy do work while we probe its edges. And if the opening chapter ran faster, the pen we already hold might still be the one that wrote it, just with finer strokes than our first sketches allowed. Star factories at dawn. To make those early overachievers plausible, you have to walk inside the machine rooms that light them up. Not the polite, regulated factories we see later, but metal-poor cauldrons where gas collapses violently, fragments hard and burns fast. At dawn, the chemistry is simple. Hydrogen and helium dominate. Metals are scarce to non-existent. That matters because metals are the universe's coolant. Without them, gas struggles to shed heat, so collapse stalls unless a few narrow channels, molecular hydrogen lines, and later fine-structure cooling from the first trace carbon and oxygen open the valve. When they do, fragmentation goes nonlinear. Clouds don't form a neat handful of stars, they shatter into swarms. In those brief windows, star formation efficiencies spike. A single cloud converts a shocking fraction of its mass into stars before feedback slams the door. Feedback is the throttle and the turbo. Massive newborns pour ultraviolet radiation into their surroundings, carving HII regions that overpressurize and compress adjacent gas. Supernovae follow on short fuses, millions of years, not tens, punching shocks that both disrupt and perversely trigger collapse along their shells. In clean gas, even modest enrichment multiplies cooling routes. One blast seeds the neighborhood, the next generation forms faster. Enrichment is a stair step, not a ramp. Every step shortens the clock. Black holes enter early as impatient foremen. If the first stars were truly massive, hundreds of solar masses, some die into hefty remnants that start accreting immediately. In pockets where gas collapses quasi-isothermally without fragmenting, aided by strong Lyman, Werner backgrounds that suppress molecular hydrogen, or by dynamical inflows, direct collapse black hole seeds may form at 10·4·10·5 solar masses in a single gulp. Either way, a seed that lights up at Eddington or super Eddington rates bathes its host in X-rays and mechanical energy. That sounds like a quench. Sometimes it is. But anisotropic outflows and clumpy media create channels where feedback compresses cold filaments while venting through low-density chimneys. The result can be burst, clear, refill cycles that net more stars, not fewer. Simulations compress all of this into subgrid prescriptions, rules that stand in for chaos below the resolution limit. Early on, those prescriptions were tuned to Z12 disks, not Z10 knots. Retuning means letting cold streams penetrate halos without being thermalized wholesale, allowing star formation to be burstier and more stochastic, coupling feedback preferentially along paths of least resistance instead of isotropically, and boosting metal line cooling immediately after the first enrichment events. Do that, and you manufacture compact stellar cores quickly, then puff them with subsequent heating. the kind of structural evolution JWST hints at. There's a selection trick baked in that amplifies our impression. In a universe where most early systems are small and dim, surveys preferentially find the tail, starbursts caught at high specific star formation rates, or lensed overperformers that masquerade as comet. Catalogs fill first with the loudest factories, the ones mid-burst, mid-outflow, mid-glow, while the quiet majority waits below thresholds. That bias doesn't forgive the tight timeline. It explains why we meet the sprinters before the pack. But even after debiasing, the ledger points to efficiency. Metallicity indicators, oxygen lines relative to hydrogen, rest frame UV slopes corrected for dust, imply quick cycling from pristine to enriched. Nebular line equivalent widths push absurdly high in some spectra, screaming young, hot, and dense. Rest optical continuum, when pinned by spectroscopy, sits stronger than naive models predicted for ages that young. If you're keeping score, those are three independent dials pointing the same direction: short depletion times and fast recycling. What about the initial mass function, the statistical mix of stellar masses? If it were top-heavy at dawn, with more massive stars than the local IMF, you get more light per unit mass and faster enrichment. That helps ease mass inferences and speeds the chemistry. There's risk in leaning too hard on it. A wildly different IMF would ripple into reionization budgets and supernova rates that other data constrain. The reasonable middle is mildly top-heavy in extreme conditions, then settling toward local once metals rise. Several groups have tested that knob. It buys time without breaking later checks. Black hole seeds reappear when you follow the light's edges. AGN contamination can inflate stellar mass fits and mimic maturity. Careful SCD modeling and X-ray limits peel off some imposters. A residue remains where AGN and stars cohabit. In those, the AGN isn't a mistake. It's part of the growth story. Coevolution kicks earlier than we thought, with bulges and black holes racing each other up the hill. There's a darker lever, too: gas supply. Cold streams from the cosmic web can feed halos continuously at high redshift, threading filaments straight through hot halos that haven't had time to stabilize. If the inflow rate outruns outflows, the tank stays full. Sufficiently dense inflows overwhelm feedback intermittently, lighting repeated bursts. In simulations with adaptive refinement, you can watch the braid. Filaments deliver, clumps form, winds vent sideways, and the dance repeats. Put it together and the picture shifts from miracle to method. Metal-poor gas that cools in spurts. Fragmentation that flips from reluctant to rampant. Feedback that compresses as much as it clears. Seeds that stir the pot instead of just boiling it off. Subgrid rules that stop smoothing the very chaos that makes early assembly fast. The factories at dawn don't need magic. They need permission to be messy. And when you grant that permission, the tension with lambdictum relaxes without dissolving. You still want a slightly shorter clock if the Hubble tension resolves that way. You still welcome modest nudges from initial conditions. But the heart of the fix lives where it always does in astrophysics. In the physics of gas under pressure, given too much gravity and not enough time. The Hubble tension and a shrinking timeline. While those star factories were doing overtime, another clock on the wall started ticking louder. It wasn't in a galaxy image. It was in the numbers we use to convert redshift into time. The question sounds dull. How fast is the universe expanding right now? The answers refuse to agree. And if the faster answer is right, the early universe had less time than we thought, which perversely helps explain why early light looks so intense. Here's the split. One camp anchors the present expansion rate, h, in the early universe. Start with the cosmic microwave background, measure those acoustic peaks, evolve a lambdictum model forward, and you get a present-day h around 67 kilometers per second per megaparsec. Add baryon acoustic oscillations and you tighten the leash. It's self-consistent, elegant, and model-tied. The other camp measures distances directly in the nearby universe. Build a distance ladder, calibrate Cepheid variables in galaxies with precise parallax. Use them to calibrate Type Ia supernovae. Read the slope of the Hubble diagram. That ladder lands closer to 73. Switch out Cepheids for the tip of the red giant branch and you still land high. Use an entirely different technique, time delays in gravitationally lensed quasars, where variations in the quasar's brightness arrive on staggered paths, and you get values that join the local choir. Independent instruments, different systematics, same refrain, faster. This mismatch has a name the field can't shake, the Hubble tension. It's not a rounding error. As analyses improved, the gap didn't melt, it hardened. People went hunting for shared biases. Cepheid crowding, dust laws, metallicity corrections, sample selections. Tip of the giant branch calibrations to avoid the same pitfalls. Strong lensing teams built careful mass models and long campaigns to measure delays. Each method trimmed its own hedges. The tension stayed, and in 2025, new time delay results from teams in Tokyo strengthened the late time case for a higher H, independent of the traditional ladder. Why does a higher H help our dawn problem? Because a faster expansion today shrinks the inferred lookback time to a given redshift under the same model. The road marker, z equals 10, sits a bit closer to us in clock time if the local H is larger. That doesn't magically turn dwarf clumps into massive galaxies. It buys breathing room. A timeline shaved by tens of millions of years at high redshift isn't everything, but it eases the pace those factories must keep. The harder question is what physics could reconcile both camps without sleight of hand. One family of ideas tweaks the early chapter, before recombination, so that the sound horizon, the physical size of those acoustic ripples, is smaller than lambdictum assumes. Early dark energy is the headline version, a brief injection of energy density that spikes the expansion rate for a moment, shrinking the ruler. Keep the CMB peaks in place with a shorter ruler, and the same observed angles imply different distances later. Then you can raise H to match the local universe without wrecking the microwave sky. Variants play with additional relativistic species, altered neutrino physics, or features in the inflationary potential. All aim at the same lever. Change the calibration of the early yardstick so the early and late measures meet. Skeptics ask for receipts. If you add an early energy component, you can't overproduce small-scale structure or mangle recombination. If you add radiation, you affect nucleosynthesis and the CMB damping tail. The viable models thread narrow corridors between datasets. Some make it through, many don't. That's progress, not failure. The data prune the garden. Meanwhile, the local side keeps cross-checking. JWST has joined the distance ladder game, refining Cepheid photometry in crowded hosts with sharper resolution. Some calibrations nudge numbers slightly but don't settle the fight. Strong lens time delays, fully independent of the traditional ladder, continue to prefer a high H, reinforcing the discomfort. A few analyses find values that lean modestly lower. The overall picture still splits early versus late. There's a tempting narrative trap here. Declare the early universe wrong because the local methods feel more direct, or declare the latter suspect because the CMB suite is so clean and global. The honest view is less romantic. Each approach measures something real, filtered through assumptions. The tension is a diagnostic, not a verdict. It points to one of two outcomes. Either a subtle, shared systematic still hides in plain sight across multiple late-time probes, a tall claim. Or we've learned that the simple lambdictum story needs a small preface, a tweak to the opening paragraph that leaves the rest of the book intact. If the latter wins, the too big, too soon refrain softens again. A shorter sound horizon and a faster inferred H compress the timeline, making elevated early efficiency look less miraculous and more necessary. Those galaxies remain overachievers. The universe stops being broken and becomes tight on time with a more complicated prologue. Here's the human moment. A lensing team spends years chasing 4 images of a quasar that flickers with chaotic grace. The delays settle. The model holds. Their H lands high, and they know they've just made somebody's night and somebody else's rebuttal. Across the world, a microwave background analyst refits an early dark energy model against the damping tail and admits it almost works, but not quite without strain. Both publish. Neither declares victory. The clock on the wall keeps ticking, and the dawn galaxies keep shining, daring the timeline to catch up. Dark energy, dark matter, friends or suspects. If the clock might be off, the next suspects are the two actors that never show their faces. Dark matter builds the scaffolding, dark energy stretches the stage. For decades, they've been the reliable background players that make the plot work. Now the opening chapter feels tight and everyone wonders, are they still just friends, or did one of them nudge the prologue? Start with dark energy, the lambda in lambdictum. In its simplest form, it's a cosmological constant, a fixed energy density of the vacuum that doesn't dilute as space expands. That single term explains late-time acceleration, fits supernova distances, and with Bow and the CMB, sets a clean geometry. The constant version is stubborn and simple. It also leaves no room to massage the early-time yardstick without adding extra pieces. So theorists ask if lambda could be a field that changes slightly with time, quintessence, or an episode of early dark energy that spikes before recombination, then fades. Those aren't free lunches. An evolving component must pass the CMB's tight checks, avoid spoiling nucleosynthesis, and keep galaxy clustering in bounds. The viable corners are narrow, but not empty. A brief early pulse can shrink the sound horizon just enough to soothe the Hubble tension, then hand the baton back to an effectively constant lambda later. If that's right, the dawn timeline contracts a little and the first lights look less miraculous. Not easy. Possible. Now turn the other dial. Dark matter is the growth engine. Give gravity something cold, invisible, and nearly collisionless, and it collapses into halos early, pulling gas along. The spectrum of initial fluctuations, more power on small scales or less, sets how quickly those halos assemble. Within current bounds, you can tweak the tilt of the spectrum and the amplitude sigma aid a hair and speed small-scale collapse. You can't go wild without smashing the CMB peaks or lensing statistics, but you can lean into the edges. Warm dark matter, particles with a little thermal kick, would do the opposite, smearing out small scales and making early assembly harder. That's the wrong direction for our problem. Self-interacting dark matter reshapes halo cores and satellite distributions, helpful for some galactic puzzles, but neutral for the dawn factories unless the cross-section is tuned to change inflow geometry. The headline remains: cold, mostly collisionless dark matter is the right tool for fast early structure, provided you let the baryons use it well. Inside that scaffold, small parameter shifts matter. A slightly higher sigma-8 pushes more halos over the threshold for rapid cooling at high redshift. A modestly higher baryon fraction feeds denser disks that fragment harder. You can adjust within observational fences and raise the odds of catching luminous sprinters at Z 1013 without wrecking low redshift clustering or weak lensing. But each nudge pays rent everywhere. Too much small-scale power and you overproduce satellites. Too much baryon density and you bump the CMB damping tail. The virtue of lambdictum is that it ties your hands gently. The vice is that it ties them. What about the chemistry and light we measured? Enhanced early cooling through even trace metals accelerates baryons regardless of dark sector tweaks, but the timing of those traces depends on how quickly halos form and merge. A slightly quicker halo assembly, courtesy of an allowed upward tilt or amplitude, cascades into faster enrichment and brighter rest optical light, which is exactly where the tension sits. Meanwhile, if dark energy briefly intervened pre-recombination, the ruler shrinks, the distances retune, and the clock tightens. Two small moves, separately constrained, that both help. Here's where the suspects earn their names. Change too much and everything else breaks. The constant lambda has passed 1,000 consistency checks, making it dynamic invites new ones. Cold dark matter explains the CMB peaks, Large-scale structure, lensing, and cluster abundance. Trading it for something exotic usually harms early assembly, not helps it. The honest middle is flex, not flip. Within lambdictum elasticity, you can bend but not snap. And yet, even with modest bends, some stubborn signatures at dawn still insist on efficient baryonic physics. High equivalent width lines pointing to young, dense regions. Compact stellar cores that imply violent inflows. AGN that show black holes and bulges racing together. Dark matter and dark energy set the lanes. The baryons did the sprint. So are they friends or suspects? Both. Dark energy may have whispered early, then gone quiet. Dark matter remains the workhorse, with small allowed parameter moves tilting early growth. Together, they frame a universe that can deliver bright juveniles on time if the gas plays fast and messy. The crisis doesn't ask you to fire the background players. It asks you to check if one delivered an extra line in the cold open, and whether the other stood a little closer to the spotlight than the rehearsal notes said. Voids, cold spots, and missing texture. Swing the camera from crowded proto-cities to the places that look forgotten. Out in the Boots void, you can fly hundreds of millions of light years and count galaxies on your fingers. On a first pass, it feels like someone missed a render pass, like a texture pack failed to load. But emptiness isn't a bug in a universe that grew from ripples. It's what gravity does when it drains the basins and piles matter on the rims. Start with how the web forms. Inflation lays down tiny over and under densities. Cold dark matter amplifies both. Over densities grow into filaments and knots. Under densities evacuate, pushing material outward and swelling into voids. Simulations seeded with near Gaussian initial conditions routinely spit out vast hollows, rare but allowed. Survey teams slice wedges through the sky and watch the dots thin, then vanish, then reappear as walls on the far side. The statistics match what lambdictum predicts for a universe that likes contrast. The eye expects wallpaper, nature prefers relief. Those emptinesses aren't silent either. They're clean laboratories where galaxies evolve with fewer flybys, slower harassment, and gentler tides. Gas can trickle, disks can stay cold, and star formation can dawdle. If you're hunting for breaks in the code, voids offer a trap. A giant hole doesn't mean missing physics. It usually means the recipe worked. Rare isn't wrong. Rare is part of the distribution. Then your attention catches on a different kind of absence, a cool blotch on the oldest light we have. The cosmic microwave background maps look like static until you plot their power spectrum. Then they look like a drum carved by sound. Overlay that neat pattern onto the actual sky, and there's a patch a few degrees wide that runs colder than average. Analysts dub it the cold spot and spend years testing the obvious outs, foregrounds. You model and subtract dust and synchrotron. Survey masks. You rotate and reweight, it persists. One physical way to lower a patch's temperature is the integrated Sachs-Wolfe effect. Photons that cross a large, evolving under density can lose a little energy if the potential wells are changing as dark energy accelerates expansion. Stack galaxies along the cold spots line of sight, and you do find an extended underdensity, a supervoid, big enough to matter. The debate is whether it's big enough. Some reconstructions say the void accounts for part of the dip, not all. Others argue the combination fits within noise. Either way, the anomaly's significance lives in a gray zone, provocative, not definitive. Here's where the missing texture metaphor can steer you wrong. The microwave background is a random field with well-measured statistics. In any finite realization, you expect peaks and dips. If you pick the deepest dip after looking, its rarity is less shocking than the headline suggests. The look elsewhere effect is relentless. The honest move is blind tests. Define your statistic before you see the map, generate many fake skies, and count how often you get a patch as cold. Those exercises tend to deflate drama, not to zero, just to modest. This isn't permission to shrug. Anomalies are useful because they force you to audit the pipeline. Are beam asymmetries sneaking in? Are component separation methods correlating noise across scales? Are your masks biasing multipoles? Teams reprocess with different algorithms and instruments, WMAP, Planck ground-based polarization maps, and watch the cold spot wobble but not vanish. It ends up as a Rorschach test. If you want a relic from pre-inflation, you can squint and see it. If you want Gaussian luck, you can quote numbers and move on. Meanwhile, the broader consistency checks keep earning their keep. The void size function, the distribution of void sizes, leans on the same initial power spectrum that sets filament strength. Observed catalogs agree with simulations within sensible bounds. Lensing across voids measures their mass deficits. The signals line up. Cross-correlations between microwave maps and large-scale structure detect an average integrated Sachs-Wolf imprint, as expected in a lambda-dominated universe. The missing texture, in other words, looks more like compression than deletion. You don't store many bits in empty interiors. You encode structure at the boundaries. There's a human moment in this quiet science. A grad student builds mock skies, planting artificial supervoids with different profiles. She ray traces microwave photons across them and measures the temperature decrements. The curve creeps toward the observed dip and stalls. Her advisor shrugs. Good. Now you know the limit of that lever. Across the hall, a void finder runs on a spectroscopic survey and flags a new hollow. They plot its edges, then its galaxies. A handful drift inside like campfires in a desert. It's not a mistake, it's the desert. If you're keeping our running theme in mind, the lesson is familiar. Where signals can travel, redundancy stabilizes facts. Filaments blaze with photons and get copied into many channels. Voids hold fewer messengers, they're low information by design. A cold patch that survives blind tests might whisper new physics. Most will settle into statistics. Until a pattern repeats, across instruments, across methods, with a significance that grows as you add data, the disciplined read is restraint. And yet one useful shift does land. Seeing emptiness as a feature changes how you search. You stop demanding uniform coverage and start asking what the edges tell you. In a holographic-leaning cosmos, boundaries matter most. Voids aren't unrendered. They're cheap on storage. The render cost shows up where the walls rise, where the gradients sharpen, where the light can carry a message and be heard. Quantum to classical, the universe locks in. We've been staring at structure, the web, the voids, the bright juveniles. Now zoom down into the rule that lets any of it become a stable fact. The universe doesn't wait for eyes. It waits for information to spread. When it does, possibilities stop interfering and start behaving like history. Down in the lab, the pattern shows up with cruel reliability. Send electrons through two slits and you get fringes until which path information leaks. Photons scatter off the edges. A molecule in the air jostles the beam. A detector clicks. The interference evaporates because the electron has become entangled with an environment that now carries a record. That's decoherence. It's not consciousness. It's bookkeeping. Amplitudes that once added now separate because their correlations have been broadcast into too many degrees of freedom to reverse. Scale that to the sky. Inflation stretched quantum fluctuations to cosmic size, but stretching isn't yet selecting. The lock-in happens as those modes interact with an enormous bath, photons, neutrinos, gravitons, and with each other under gravity. Modes that re-enter the horizon couple to the photon, baryon plasma. Their phases get imprinted in acoustic oscillations, then further copied as free-streaming photons carry the pattern across the sky. By the time recombination finishes, the microwave background isn't a superposition you could revive. It's a mural written redundantly in light. Quantum Darwinism turns that mural into a rule. Facts become objective when many fragments of the environment independently encode the same information. A dust grain's position is plastered into zillions of optical photons. A galaxy's mass distribution is stamped into weak lensing shears, X-ray gas, and thermal Sunyaev, Zeldovich signatures. Observers don't agree because they compare notes. They agree because they are reading different copies of the same environmental record. Objectivity is redundancy. The time scales are brutal. For macroscopic degrees of freedom, decoherence is effectively instantaneous. A micron-sized particle in air loses off-diagonal coherence for positional splits larger than optical wavelengths in about 10⁻31 seconds. In the early universe, number densities and coupling rates make the bath even more intense. The selection of pointer states, stable variables that survive environmental monitoring, happens far faster than any dynamical evolution we care to measure. In cosmology, those pointers are curvature perturbations with definite phases. Later, they're densities, temperatures, velocities. The variables you use in fluid equations are the ones the universe naturally preserves. So why does this matter for too big too soon? Because lock-in sets the rules the factories at dawn must follow. You can't rely on delicate quantum phases to coordinate collapse across cosmic distances. Causality and decoherence shut that door. Early efficiency has to come from classical channels, cooling routes, shocks, inflows, feedback cycles. The lock-in is why our fixes lived in messy gas physics instead of magic coherence. There's another stake. Horizons act like moving interfaces that gate what can be stabilized. Inside your particle horizon, signals can circulate and records can proliferate. Outside, nothing you do can copy information back to you. That's why the map of your universe is a mosaic assembled at light speed. It's also why the render cost is paid at boundaries. Facts that cross horizons, like CMB photons, become keystones of objectivity because their copies arrive from everywhere. Consider a micro story. A delayed choice quantum eraser in a basement lab toggles whether which path information is preserved after photons have already hit a screen. The interference returns in the sub-ensemble where the information is erased, but never globally. The lesson holds upstairs. Context determines which histories can recombine. In the cosmos, the context is an ocean of environment that never forgets. Once primordial modes are broadcast into the microwave sky, there is no sub-ensemble large enough to stitch them back. Lock-in also explains why anomalies are hard to trust. A genuine pre-inflation relic would need to survive relentless environmental monitoring and the averaging of cosmic variance. Most features that look special wash out because the sky is a master copier of typicality. When something persists, the acoustic peaks, the hemispherical asymmetry bounds, the exact blackbody, they persist because they are supported by vast redundancy. There's a thermodynamic price tag on all of this. Landwehr's principle says erasing one bit of information dissipates at least kT ln2 of heat. Turning quantum possibilities into classical facts isn't literally erasure, but the growth of entanglement and the proliferation of records increase entropy. The arrow of time in structure formation aligns with a monotonic growth in environmental bookkeeping. Galaxies remember their past not because stars keep diaries, but because the universe keeps copying their traces into photons, neutrinos, and tidal fields. Reversing that would require erasing every copy, a cost the cosmos refuses to pay. If you're keeping the ledger theme in mind, lock-in is the moment an entry goes permanent in your causal patch. Before selection, amplitudes are cheap and reversible. After, records are expensive and sticky. That's why late-time tweaks, reinterpreting photometry, correcting lensing, only move masses within error bars. The underlying classical facts are hard set by a billion environmental witnesses. And here's the pivot forward. If the universe stabilizes facts through redundancy inside horizons, then the ultimate limits on what can lock in, and how quickly, are set by those horizons. Finite patches imply finite storage and finite bandwidth. The next move is to treat horizons as the interfaces they are, boundaries that budget how much can ever be rendered into history. Horizons as interfaces, your bandwidth budget. If decoherence is how facts lock in, horizons decide how much can ever be locked in for you. Think of them less like walls and more like interfaces, APIs with rate limits. They don't stop the universe from existing beyond them. They bound what your patch can address, copy, and stabilize as shared record. Start with three edges people conflate. The particle horizon is the farthest distance from which light could have reached us since the hot beginning. It's a time limit. Every day, more photons slip in from just beyond yesterday's edge. The event horizon is harsher, a future boundary. In an accelerating universe, there's a shell beyond which signals launched now will never reach us, no matter how long we wait. The apparent horizon is local and momentary. The surface where outgoing light rays hover on the brink between moving outward and being dragged back by gravity, defined by the flow today and by your motion. Different questions, different edges, different answers. Each horizon carries thermodynamic bookkeeping. In a dark energy-dominated cosmos, the de Sitter-like event horizon has a temperature, the Gibbons-Hawking whisper, and an entropy proportional to its area. That area law is the same hint black holes shouted. Count bits on surfaces, not volumes. Translate that into everyday language and the message bites. Your causal patch has a finite storage budget. There is a maximum number of distinct, retrievable degrees of freedom that can ever be stabilized inside the horizon that defines your instance of the universe. That doesn't mean you only get a sparse world. Redundancy works in your favor. Most of the bits inside your patch aren't unique microstate labels. They're many copies of the same macroscopic facts. That's why you and I agree on the positions of planets without swapping wave functions. Photons, neutrinos, and gravitational fields broadcast the same story across countless channels. Objectivity is expensive by repetition, not by novelty. The horizon's area bound tolerates it because the ledger doesn't charge the same for new entries and for copies of old ones. Now layer in bandwidth. Light speed caps how fast information moves. Expansion stretches the grid you're trying to cross. Within your light cone, you can coordinate, entangle, and compare. Beyond it, requests never arrive and responses never return. That's why the observable universe isn't a dome you stare at. It's a mosaic you assemble as signals reach you. It's also why rendering belongs at boundaries. Facts that can, in principle, be copied into your wedge are the ones that become part of your history. Everything else is cached elsewhere, real, but out of reach. Microstory. A team models light propagation near the apparent horizon of a de Sitter patch and watches signals redshift toward oblivion as they approach the edge. The photons never vanish in the math. They dilute, stretch, and drown in the thermal bath. The plot looks like a slow fade to static. Someone circles the entropy term on the board and writes, "Quota enforced." Holographic hints sharpen this. In toy universes where we can do the math cleanly, the entire bulk physics is encoded on a lower dimensional boundary. Our world isn't that toy, but the refrain repeats. Area counts, surfaces encode, volumes emerge. If that spirit carries over, then the richest descriptions you can ever access live on cuts, on horizons and screens, while interior detail is an efficient consequence. You don't need a voxelated storage of every cubic centimeter. You need enough boundary data that any bulk question you can physically ask has a definite answer when asked. This reframes a few of our tensions. The particle horizon's tide of new photons is literally your bandwidth increasing with time. Each arrival adds to your public record. The event horizon's existence tells you there's a finite maximum to how much you'll ever collect. The apparent horizon reminds you that interfaces depend on who is asking, drift differently, and your dashboard shifts. Observers in different states of motion slice the same world into different retrievable caches without contradiction, because no one can query all slices at once. Landor sneaks in with a receipt. Erasing information costs heat. Stabilizing facts via redundancy raises entropy. The ledger balances by exporting the cost to baths, radiation fields, matter, horizon temperatures. That's why reversing classical history is practically impossible. You would have to erase every environmental copy up to the edge. The horizon's temperature is a standing fee for access. The entropy bound is your storage cap. What does this mean for galaxies at dawn? It puts a hard ceiling on magical coordination. You can't appeal to conspiracies beyond causal contact to build structure faster. You can appeal to efficient, local physics that broadcasts its results into your wedge early and often. It's not that the universe won't render beyond your reach. It's that your story renders where signals can travel, where boundaries can encode, and where the budget allows the copies to stick. Black hole bookkeeping, no bit left behind. If horizons are interfaces with budgets, black holes are the auditors who never forget a line item. They look like erasers, swallowing stars and light, but the longer you sit with their math, the more they behave like accountants, obsessed with balancing every bit on the books. Start with Hawking's shock. Take a quiet black hole, let quantum fields ripple near its horizon, and particle pairs appear in the story. One partner falls in with negative energy, the other escapes as thermal radiation. The hole shrinks. The spectrum looks memoryless, like heat from a fire that doesn't care if you burned a letter or a leaf. If that's the end, information dies with the horizon. Unitarity, the core promise that quantum evolution preserves probabilities perfectly, breaks. Physics flinches at that. Then Page reframed the question as a curve. If evaporation is unitary, the entropy of the outgoing radiation should rise early, because those first quanta are entangled with the interior, reach a peak at the Page time, then fall as later radiation carries away correlations that let you, in principle, reconstruct what fell in. Hawking's original calculation gave a straight climb to the end. The paradox crystallized as a mismatch between two plots. The way out came from a surprising direction: geometry learning to count like quantum theory. In tools built from holography and quantum extremal surfaces, you compute the entropy of the radiation not by naively tracing out the interior, but by allowing islands, regions that lie behind the horizon, to be included in the radiation's entanglement wedge if doing so minimizes a certain generalized entropy. Early on, the island is absent. Entropy rises. Past the Page time, the island appears. Entropy bends down. The Page curve emerges from gravity itself once you let entanglement shape what counts as outside. The ledger balances. No bit is lost. It's recoded in correlations that seep outward. That fix raised a fiercer question at the edge. If late radiation must be highly entangled with early radiation to lower entropy, how can it also be maximally entangled with a partner just behind the horizon to keep the crossing smooth? Monogamy of entanglement says you can't have both. The firewall argument sharpened that into a dilemma. Either unitarity wins and the horizon burns, or smoothness wins and information dies. Neither option felt right. The response didn't arrive as a loophole, but as a new way to think about where things are. In holographic codes, bulk operators can be reconstructed from different boundary regions depending on the global state. Interior modes aren't independent objects stored in a separate room. They're encoded redundantly in the same boundary degrees of freedom that also encode the radiation. State dependence and quantum error correction let the same logical qubit be recoverable by different coalitions without duplication. Complementarity adds the causal slice. No single observer can verify both the smooth horizon and the detailed structure of the decoded radiation. For an infaller, the horizon stays dull. For a patient decoder at infinity, the message lives in the heat. No contradiction appears within any one world line's access. There's a practical punchline in a thought experiment with a diary. Toss a small quantum system into an old black hole, one past its Page time, and ask how long you must watch the Hawking glow before the diary's information starts to come out. The Hayden Preskill result says the hole acts like a fast scrambler. After a scrambling delay that scales like the horizon radius times a logarithm, the outgoing radiation begins to encode the diary. In principle, with impossible control, you could retrieve it. In practice, the computation is astronomical. The ledger is unitary but not generous with shortcuts. Soft hair proposals add edge detail. Subtle conserved charges and asymptotic symmetries, the BMS dressings of gravitational fields, store extra labels on the horizon itself. They don't by themselves carry the whole book, but they enrich the interface, turning a bland surface into one with memory. Combined with back reaction and the dressing that ties every excitation to the metric it disturbs, the divide between inside and outside blurs further. The moral repeats, boundaries encode, and the interior is a story told through accessible correlations, bounded by who can ask what. If you hold our rendering metaphor, the lesson is clean. The universe doesn't delete alternate histories. It hides them in entanglement that can't be accessed within a single local frame. Rendering, a classical outcome, is stabilizing one branch with redundancy while weaving the rest into correlations that remain off-limits for you. Horizons don't trash the manual. They compress it, turn volumes into surface books, and invoice you for any attempt to read them. Fold that back into the cosmological horizon we actually live with. Our patch has a temperature, an entropy, and an interface that enforces quotas. If black holes are honest auditors locally, de sitter, like horizons play the same role globally. No bit left behind isn't a slogan, it's a constraint. It's why early facts, acoustic peaks, bright juveniles, compact cores, must be explainable by physics that can be copied into our wedge. It's why conspiracies beyond our light cone are off the table. The ledger will balance at the edge every time. The crisis without the hype. Let's clear the table and count what actually changed, and what didn't after the first wave of panic. Those universe breakers we met at dawn. Spectra pulled some down in redshift, sliced others' masses, and flagged a few AGN wearing stellar light like a coat. Strong lensing stretched headlines. Selection favored the loud tale. When the dust settled, the miracle faded into a tighter schedule with brighter overperformers than baseline lambdictum had sketched. That's not a collapse. It's a recalibration. What still stings? A crowded bright tail even after careful fits. Number densities of compact, relatively massive systems that sit above many simulations. Line equivalent width so high you wince. Rest optical continuum stronger than naive ages suggest when pinned by spectra. Chemical hints that enrichment stepped quickly. These aren't artifacts you sweep away with one systematic, they're converging nudges. Each demands efficient physics or a slightly shorter clock, or both. Where did corrections land? Photometric redshift sorted into cleaner bins once Lyman breaks and nebular lines were measured. Masses fell when teams folded in strong line contamination, bursty histories, and AGN components. Sizes shrank after lens models improved and surface brightness biases were accounted for. The sum of those edits shifted several poster children from impossible to impressive. But the ledger didn't zero out. A residual tension stayed. Fewer headliners, still too many sprinters. What do these holdouts actually break? Not the CMB acoustic peaks, not baryon acoustic oscillations, not supernova distances. Those anchors remain welded. The crisis lives in a narrower alley, early efficiency versus the time budget. That's why the clean read is binary in the best sense. Either the early universe chapter carries an extra line, an early dark energy pulse, a small tweak to the sound horizon, a permissible tilt in the seeds, or the formation channels at high redshift are sharper, faster, and more burst-prone than our mid-redshift-tuned subgrid rules allowed. Neither move asks you to throw out lambdictum. Both ask you to flex it where it's elastic. Here, S what the model absorbed without flinching. Modest increases in star formation efficiency in dense halos. Immediate metal line cooling once the first enrichment events occur. Bursty, anisotropic feedback that clears along chimneys and compresses elsewhere. Cold streams that penetrate and refill. Mildly top-heavy IMFs in extreme pockets that then relax. Slightly higher small-scale power within current constraints. Stack those and your simulation spit out more luminous juveniles on time. You didn't rewrite gravity. You stopped smoothing the chaos. And here's what it didn't absorb yet. An IMF so extreme that reionization and supernova statistics break. Warm dark matter that smears the very scales you need. A wildly evolving dark energy at late times that shreds the supernova and bow fit. The surviving fixes live where the data leave room. A brief pre-recombination nudge that shrinks the ruler, or astrophysics that sprints. Meanwhile, the Hubble tension keeps humming in the background. Local ladders and strong lens time delays prefer a higher H, early time inferences prefer lower. If an early dark energy haircut shortens the sound horizon, both camps can meet without wrecking the microwave sky. That shaves the clock between us and Z10 by enough to soften, not solve, the dawn pace. It's not a magic wand. It's breathing room. So is there a crisis? If by crisis you mean the standard model shattered, no. If you mean a productive mismatch that pries open new physics or sharper astrophysics, yes. The field's response says everything about which definition we're in. Teams didn't retreat to press releases. They reprocessed photometry, scheduled spectroscopy, rebuilt lens maps, rewrote subgrid prescriptions, and stress-tested early-time tweaks against nucleosynthesis, damping tails, and structure growth. The result is a trimmed list of real tensions with plausible levers, not a bonfire. Here's a human audit that keeps me grounded. An observer who once tweeted too big, too soon, now presents a spectrum that knocks her favorite candidate down a peg and calls it still fast, now cleaner. A simulator who once waved away the tail now shows a run that, with updated feedback and cold stream treatment, populates it, then admits it overshoots satellites at Z and needs taming. A CMB analyst who dislikes early dark energy still concedes a narrow corridor survives every test and might be where reality lives. Nobody burns the book. Everybody edits their chapter. Strip the hype and the story reads like this. JWST didn't falsify the Big Bang. It forced us to read the opening pages more carefully. The acoustic peaks still ring. The large-scale web still matches. Supernovae still trace acceleration. And yet, the first luminous structures arrived at a pace that pushes either the early calibration or the physics of gas to their efficient edges. That's not a contradiction, it's an invitation. The next steps aren't think pieces. They're measurements and models that decide whether the age nudges, the seeds tilt, or the factory simply ran hotter than we assumed. And if the age nudges, the crisis becomes a recalibration with better clocks. Alternative frames, no magic, just tests. When the schedule gets tight, it's tempting to reach for big rewrites. Resist that. The only ideas worth keeping are the ones that pay rent across independent datasets. No magic, just tests. Start with early dark energy, the cleanest surgical tweak. Picture a brief pulse of vacuum-like energy before recombination. It speeds expansion for a moment, shrinks the sound horizon, then fades so late-time geometry still looks like lambda. That haircut lets the CMB keep its acoustic peaks while raising the locally inferred H, easing the Hubble tension and shaving the dawn clock. It sounds neat. The checks are hard. You can't spoil Big Bang nucleosynthesis, distort the CMB damping tail, or overgrow small-scale structure. Teams fit eta against Planck polarization and lensing, bow, and supernova distances. Narrow corridors survive, many die. That's progress. The models that live predict subtle shifts, slightly altered early growth, tiny changes in lensing, now in reach of upcoming surveys. Next are modified initial conditions. Inflation's pen can write features into the primordial spectrum, a small break, a bump, gentle running of the tilt. Within current limits, a modest enhancement at the scales that seed the first halos boosts early collapse without wrecking the CMB. Non-Gaussianity could do similar work, more rare peaks for the same variance. But here the guardrails bite. Planck's bounds on local non-Gaussianity are tight. Any help must be small. The test is clean. Measure small-scale clustering and 21-centimeter structure at high redshift. If seeds were tweaked, the pattern of early halos and the timing of reionization shift in specific ways. No headlines yet. The data are coming. Then there are exotic proposals that won't die. Tired light, static universes, steady states rebranded. JWST's early Galaxies gave these an algorithmic boost online. The tests don't care. Tired light fails time dilation in type Ia supernova light curves. They stretch with redshift exactly as expansion predicts. It fails the CMB. A near-perfect blackbody sky with acoustic peaks is not a scattering fog. It fails surface brightness scaling. Static models can be patched with new knobs, but every patch collides with bow, with lensing, with the baryon census. These aren't persecuted ideas. They're measured and found wanting. For completeness, a 2024 paper by Lior Shamir argued that JWST photometry favors tired light, but the claim conflicts with supernova time dilation and CMB constraints and has not been accepted by the broader community. Modified gravity sits in the wings. Could we change how gravity acts on galactic or cosmological scales to alter growth? Mondian flavors help galaxy rotation curves but struggle in clusters and in the CMB peaks without dark matter's inertial ballast. Cosmological scalar, tensor theories can mimic accelerated expansion, but precision bow and growth measurements corner them. For our problem, fast early assembly, most deviations slow small-scale growth or add late time quirks. You can write careful models that hide in current errors. The tests are straightforward. Redshift space distortions for growth, weak lensing for the matter field, multi-probe fits that leave little slack. The multiverse creeps in when eternal inflation is on the table. Could bubble collisions or pre-Big Bang relics leave bruises in the microwave sky? People looked. Blind searches for circular scars and specific polarization signatures turned up nothing decisive. Conformal cyclic cosmology points to Hawking points, hot spots from evaporated black holes of a previous eon. Claims exist, independent reanalyses disagree. The rule holds. If the imprint is real, it strengthens when you change instruments and pipelines. So far, it doesn't. There's also the idea that dark energy isn't constant. A slowly rolling field, quintessence, could evolve subtly, altering distances and growth. Dacey's early 3D maps tease tensions that some read as evolving dark energy. The careful take is caution. Model assumptions can project discrepancies into WZ, even when the culprit is calibration. Still, this is testable. Combine bow, supernovae, weak lensing, and CMB lensing. Look for coherent departures that persist across probes. If dark energy drifts, the integrated signatures must align. Under all of this is a simple rule you can audit. An alternative earns time on the stage only if it fits. The CMB spectrum and lensing, bow at multiple redshifts, supernova distances with time dilation, primordial abundances, galaxy clustering and weak lensing, the reionization history, direct H constraints like time delay lenses. Move one lever and you accept every receipt. The ideas that survive this gauntlet get specific, not grand. They predict small shifts, slightly different halo mass functions at Z tilde 10, subtle changes in 21 centimeter power during the dark ages, lensing statistics that nudge. That's why the path forward is no magic. You don't pick the theory that makes a great video. You pick the one that pays rent when the instruments change, and the teams that dislike it do the analysis. Early dark energy remains alive in a sliver. Inflation with modest features can help. Evolving dark energy is on probation. Modified gravity is boxed in. Tired light is unsupported by the key tests. The rest of the work falls back where it started. Better spectra for early masses, cleaner lens models, deeper maps of structure, sharper clocks on H. The universe isn't broken. It's asking for receipts. The machines that will decide. If this isn't a crisis but a recalibration, the verdict won't drop as a headline. It'll arrive as convergence, independent instruments squeezing the same question from different angles until the slack is gone. The next decade is a relay, and the batons are already in the air. Start with Euclid. It isn't a pretty picture telescope, it's a cartographer. By mapping billions of galaxies across a third of the sky, Euclid measures two things at once: how matter bends light, weak lensing, and how galaxies clump, clustering, and bow. Lensing tells you where the mass is without asking whether it shines. Bow gives you a standard ruler stamped into structure since the plasma epoch. Combine them and you get the geometry of acceleration and the growth of structure. Two levers dark energy can't fake in tandem. If early dark energy shaved the sound horizon, Euclid's wide map will see the ripple, a slightly different ruler imprinted at multiple redshifts and a subtle tilt in how structures swell with time. If dark energy is just lambda, the curves line up cleanly. No drama, just numbers that either meet or don't. While Euclid paints wide, the square kilometer array listens deep. Hydrogen's 21-centimeter line is a time machine to the dark ages, before stars, before galaxies, when the cosmic web was only a whisper in cold gas. SCA's first task is a timeline. When did the first lights switch on? How patchy was reionization? How fast did it proceed? If seeds were slightly tweaked or if early halos formed faster, the 21-centimeter power spectrum changes character. The size of ionized bubbles, the timing of heating, the scale of fluctuations. That's not a vibe. It's a literal spectrum with peaks you can measure. Tie it to JWST's counts and Euclid's lensing and you get a 3-frame film. Seeds, assembly, glow. CMB S4 brings the microwave sky into its last, sharp focus. The target everyone knows is primordial B-mode polarization, a faint curl pattern from gravitational waves launched during inflation. A detection nails inflation's energy scale and rules out swaths of potentials. A non-detection pushes more models to the margins and trims freedom at the seeds. But S4's power is broader. Exquisitely precise E-modes, lensing of the CMB by intervening structure, and damping tail constraints that early dark energy must thread. If an eta pulse tried to shrink the ruler, S4 will grade the attempt at the percent level. If the seeds hide a feature, S4's small scales turn guesswork into fit. Then there's the low-frequency gravitational wave chorus, pulsar timing arrays that hear nanohertz ripples as tiny drifts in millisecond clocks. They've already hinted at a common spectrum, likely the murmur of supermassive black hole binaries. As baselines grow, PTAs will map how often the biggest holes found each other and when. That's a growth ledger for bulges and black holes, co-evolution quantified. In a universe where early AGN helped drive fast assembly, the background's amplitude and shape become a consistency check on the bright juveniles. If the early factory story is right, the choir's volume should rise along the same timeline. These machines aren't silos. Euclid's shear maps calibrate CMB lensing. CMB lensing calibrates Euclid's growth. SCA's 21-centimeter tomography supplies the patchiness scaffold that reionization models need to translate JWST's counts into a photon budget. Time delay lenses measured from the ground pin H independently. Bow sets the ruler. Supernovae trace distances. All meet in shared parameter space. If early dark energy lives, it will wear the same outfit in every room. If inflation wrote a small feature, it will appear as a kink in S4, a nudge in early halos, a shift in reionization. The trick isn't power, it's cross-checks. The machines that decide don't vote by show of hands. They triangulate. There's a quieter revolution under the hood. Spectrographs on 8 and 10-meter telescopes are chewing through the redshift JWST photometry teased, putting Lyman breaks and nebular lines on firm ground. Adaptive optics and improved mass models are unwarping strong lenses so sizes and masses stop leaning on the same handful of assumptions. Calibrated laboratory standards, laser combs, better flat fields on sky tests are shaving systematics in ways that used to hide in the error bars. The decision won't come from one big number. It'll come from 100 small ones that finally agree. Micro story. A Euclid analyst pulls an overnight to beat down a shear bias by 0.2%. Across the ocean, a pulsar timing team adds 3 years to their baseline and watches a subtle bend in the spectrum harden. A CMB S4 engineer signs off on a cryostat that will hold polarization systematics under control. None of them tweets a crisis. All of them are turning arguments into measurements. So what decides? Not slogans about broken models. The deciding moves are specific. Euclid's growth versus geometry. CMB S4's damping tail and B modes, SKA's 21-centimeter film of first light, time delay H standing next to Bow's ruler, PTA's chorus rising with early AGN. If the opening chapter needed a faster pen, these are the pages where you'll see the stroke. And if it didn't, if the factories at dawn simply ran hot inside a lambdictum frame, these same machines will say so by refusing to disagree. The verdict won't be dramatic. It'll be boring in the best way: convergence. Life inside a compressed world. If horizons set budgets and redundancy makes facts real, then living well is about spending bandwidth where it propagates. Agency isn't magic, it's entanglement you control. You make choices that the environment can copy. Data released, code shared, instruments built, laws written, habits that outlive you because they're recorded in many places at once. Skepticism still matters, but aim it. Doubt spectacle that refuses receipts. Trust signals that survive instrument swaps and hostile reanalysis. That's how truth travels in a compressed world, through crosschecks, not charisma. Meaning scales by design, not volume. A small lab that reduces a shear bias by a fraction improves every cosmology fit downstream. A pulsar added to the timing array tightens the chorus. A catalog with cleaner systematics rewrites fewer papers but strengthens more. You don't need a megaproject to matter. You need redundancy that sticks. There's a cadence to good work under constraints. Pick questions with short feedback loops and long echoes. Build things that outlast you: archives, open simulators, public pipelines. Accept latency. Most payoffs arrive after your coherence time. That's fine. You're writing to the boundary. On the human scale, objectivity as redundancy sounds cold. It is. It asks you to make promises legible, measurable, repeatable, visible to people who don't know you. In physics, that's a spec. In life, it's accountability. A last rule: spend attention where gradients are. Arguments heat the void, measurements sharpen edges. The universe won't render where no signal can go. Don't waste your breath demanding it. Point your antennas, widen your horizon, and let new photons become public record. That's how stories harden into history. The boot versus the bang. Not proof, just a cleaner question. If boundaries encode and compression rules, the origin may have been a boot, not a bang. Fast, efficient, minimal. We'll let the next data choose. Subscribe, watch our deep dives on dark energy and black hole bookkeeping, and drop your sharpest origin test in the comments.